In the last video lectures, we have discussed different types of probability functions such as CDF, PDF, marginal PDF and conditional PDF. Now we discuss very important terms that are used in communication system for quantitative analysis, and these are expectations or statistical averages. Basically, for noise performance in digital communication, we have to find mean and variance. Variance is also called central moment. Now, for discrete random variable x, mean is represented by expectation operator and it is denoted by capital E. So, mean E function x or simply written as mu suffix x. So, in performance analysis, the mean can be determined in terms of probability mass function, that is P function x equals to small x, which represent all the possible outcomes. So, mean or expectation E function x equals to summation x P function x equals to small x. Here, small x is a real value number. And this expression is the weighted sum of all the possible outcomes. Here summation is for all values of random variable x. Similarly, for continuous random variable, the mean is represented in terms of probability density function, that is f function x. So mean or expectation of x equals to integration of product of x and function x into dx. Here small x is the assigned real number corresponding to random variable x. This expression of mean or expectation in case of continuous random variable is also called center of gravity of area under the PDF curve. So in order to find mean or expectation, we take weighted sum of possible outcomes in case of discrete random variables and weighted integration of PDF called center of gravity in case of continuous random variable. Now, second term is called variance or central moment of random variable. Here, the variance expresses the spreading of probability distribution with respect to mean value and it is denoted by sigma square or variance of random variable x. As we know that variance is the spread of probability distribution about the mean, so we take a difference term. Then sigma x square or variance of random variable x is simply written as expectation of x minus mu x square. And in terms of probability mass function, the variance sigma x square equals to summation x minus mu x whole square P function x equals to small x. And this expression can be used to determine the variance of discrete random variable. Next, in case of continuous random variable, we have probability density function, that is f function x. So variance sigma square suffix x equals to integration of x minus mu x square into f function x into dx. So with the help of mean and variance corresponding to discrete and continuous random variable, we can easily analyze the noise performance in digital communication. Next, we talk about important term called covariance. Covariance is the special case of variance in which the statistical averages between two random variables can be determined, and that can be used for the analysis purpose in communication system. So for covariance, we consider two random variables x and y, and covariance of x and y is equals to expectation of product x minus mu x, y minus mu y. Here mu x and mu y are the mean value corresponding to random variable x and y. So the expression covariance x comma y equals to expectation of x minus mu x into y minus mu y. Now, when we compare covariance with variance, we can find that in variance, we find expectation of square term, but in case of covariance, we find expectation of product of two terms correspond to two random variable x and y. Or simply says, covariance is the expected value of the product of two random variables x and y. Now we expand this expression within square bracket, and it is equals to xy minus x mu y minus y mu x plus mu x mu y. Now after taking expectation of individual terms, we get covariance of x comma y equals to expectation x into y minus mu x mu y. Since the expectation of second term, that is expectation of x into mu y, is simply written as mu y expectation of x, and expectation of x is equals to mu x. So E function x into mu y equals to mu y mu x. Similarly, expectation of y into mu x equals to mu x mu y. So the two terms of mu x mu y are cancelled and we get only one term, and covariance is equals to expectation xy minus mu x into mu y. Now in the formula of covariance, we consider x and y as continuous random variable with a joint probability density function, that is f function x comma y. Then the mean or expectation of xy, that is first term, is equals to double integration of xy into joint probability density function, that is f function x comma y into dx dy. This expression is called correlation of random variable x and y. So covariance can be determined using correlation and mean value corresponding to random variable x and y. Now we consider again x and y as statistically independent random variable having both mean mu x and mu y that are not correlated with each other, hence called uncorrelation of x and y. So in this case, expectation E function xy is equals to double integration of xy f function x f function y dx into dy. Now after rearrangement of double integration with respect to dx and dy, we get product of two terms. These integration terms can be expressed as mean or expectation. Here the first integration term is expectation of random variable x, and second integration term is simply expectation of random variable y. So in case of uncorrelation random variable x and y, the expectation of x into y is equals to product of the expectation of individual random variable, that is E function xy equals to E function x into E function y. Now after putting this value in our covariance formula, we get covariance of x comma y equals to expectation of x into expectation of y minus mu x into mu y. Or this expression is simply equals to 0 because we know that expectation of x is mu x, expectation of y is mu y. So it is understood that for uncorrelated random variables, the covariance is always 0. Or simply says covariance of independent random variable is 0. But the vice versa is not always true, which means it can't say zero covariance can find independent random variables. Now this can summarize as a point. Here the two random variables x and y are said to be statistically independent or uncorrelated if and only if expectation of xy is simply the product of their mean values. That is, in case of discrete random variables. Also for continuous random variable x and y that are uncorrelated, if joint probability density function, that is f function x comma y, is equals to the product of individual PDF, that is f function x and f function y.